Okay. That was 30, so.
All right. Well, we'll go ahead and get started on the next section, which is chapter 7. So, homework for this week. Go back to the book for a little bit. Problems 7.1 through 7.9. So those are just the book problems in chapter 7. And they'll be due next Tuesday. Okay. And so what we're talking about will be in chapter 7, which is simple harmonic motion. So, one second, I forgot one demonstration. Be right back. All right, so today we're going to talk about springs. And springs have a certain property that's a little bit interesting. First of all, as I pull down on this, the spring has to exert a force back to oppose my pulling down, right? So it exerts a force opposite the direction you pull it. In fact, if I push up, it feels like it is exerting a force downwards. Secondly, if I put one mass on here, it hangs a certain length, right? If I put on a second mass, similar type one, it goes longer, right? And in fact, if we took some measurements, we can do this. Yeah, here we are. And this, unfortunately, is not in centimeters. But it's a good demonstration ruler because it's got big numbers. So if I look at this, take a look at the length of this spring. What does it say? Can you see? Oh, let's put it this way. Length of the spring, unstretched, is about 10 inches, right? Pretty close.
Mm-hmm.
So you are drawing just the coil here.
Just the coils.
One longer.
A little under. Let's see if I can get it right. You guys see it?
Yeah.
So roughly about 10 inches. If I put on one 50-gram mass, how much is it now?
Almost 11 and a half.
Yeah. 11 and a half, well, about 11 inches. Well, wait. 11 and a half inches. So it's stretched out an inch and a half when I introduced one 50 grams. Let's put on another 50-gram thing. See what happens. Okay? So if I put on another 50-gram mass, see what it's at now. Almost exactly 13 inches. See that?
Past 13.
Well,
Well, it's
it
pretty
was
close.
at 9.5. When it was closer
Pretty-
to 9.5 when we started.
Yeah.
Yeah, it's closer
So
to 9 and, yeah, okay, so it's 13 and a half, maybe it was 9.
About
9.
2 inches each time.
Let's take it off and see what happens. I mean, be careful. Okay, so this is, yeah, you're right, it's about 9 and a quarter here on the coils. I put on one, it was 11 and maybe a quarter. If I put on another, it's about 13 and a quarter. So, no mass. That was not 9.25 inches, 50 grams, 11.25 inches, and 100 grams. Cleaning off of there, it was 13.25 inches. So if I were to plot something like this, what you'd see, well, I mean, there's only 2 data points, right? But if I added another 50 grams, you'd see that it would go another about 2 inches down. And so if I look at this, I see that I start to stretch the spring, and it seems to be that if I double the mass, I double the stretch in the spring, right? Stretch in the spring is the difference from, this is from its length with no mass. So stretch in spring is the length of the spring minus the length with no mass. With no mass. Okay, and then this is the length with the mass. So the stretch at this point was 2 inches stretch. And if I double the mass, I go up to 4 inches stretch, roughly. Pretty close. And so what we see is that it seems like the stretch in the spring, if I double the mass, or that means I double the force on the spring, right? Because the mass is hanging off of there. And it seems that if I double the mass, I double the stretch. That makes sense? So what we can say is that the spring force, the length that we stretch out the spring, will be proportional to the applied force. That's the conclusion we make. And you know, you could add more. If I wanted to do that precisely, I'd have to add a lot more in the lab, probably graph it and see whether it's a nice straight line of stretch versus force. And you see that, but if you do that, you would see that it is a nice straight line. So, what this means is that the spring force, this tells us, we've gone through what we need to know about the spring force. First of all, it's opposite the, let me just draw a picture. If I have a spring, let's put a little mass on there. If I put a mass on here, the spring stretches a little bit. This is my formula for a spring. What direction does the spring exert a force?
Opposite of the mass.
Yeah, so if I drew a picture of the little mass here, I have a spring force going upwards. That's what's keeping it from falling down. And then a gravity force going this way. And the stretch of the spring is downwards, right? The spring increases its distance downwards as I add more mass. And the spring force goes the opposite way. So the spring force will be in the opposite direction as the stretch, right? So I'm going to put a little minus sign here, getting ready to indicate that. It's proportional. I'm just going to write a constant for this. And then I'm going to write x minus x naught. These are the vectors of the end of the spring. Position vectors of the end of the spring. So this is the distance that the end of the spring has moved. This is the vector from the end of the spring. So for instance, this would be x vector, x naught vector, maybe if it was unstretched, maybe goes to here. And then this, x minus x naught, would be like this. And so you can see that that this vector here is downwards, whereas the force is upwards. Pretty much always we'll be dealing with spring forces in one direction. So I'm going to oftentimes just ignore the vector signs, and hopefully it's clear that it's just along one line, either x or y. And from context, hopefully you can get that, okay? So along one direction, say, X direction, I can say that the spring force in the X direction will be minus K X minus the unstretched spring length. So this is the length of the spring with the length of spring.
Did you put the computer down?
This is the unstretched length of spring.
What was K?
Constant.
Length of spring, yeah, 1 second. And this is a constant of proportionality between the force and the stretch. A constant. And we call K the spring constant.
Did you mute the computer?
What's that?
Oh.
It's like pi, it has an assigned number.
What's that?
It's like pi, it's a fixed number.
It's not a fixed number, it depends on the spring. Like if I have a really stiff spring, it takes more force to stretch it a certain length. So, but for a given spring, it's fixed for a given spring. Okay, does that make sense?
It's like a number that's associated with the springiness.
Yep, that's right. Stiffer the spring, the harder it is to stretch this spring, the bigger the spring constant. Okay, in fact, let's see if, well, we'll go see if we can get the spring constant for this, okay? All right. So, let's see if we can get find spring constant. All right, let's see if we can find the spring constant for this. So this thing, if I put on 50 grams, we saw it stretched 2 inches. 2 inches isn't a good SI unit, is it? So we should probably convert this to meters. Okay? And then this is 50 grams. Let's see if we can figure out the force on, let's draw a little free body diagram for that 50 gram mass. So I have a spring, and I have a 50 gram mass here. Let's see if I can draw a little free body diagram for this. What are the forces on it?
The spring force on up.
I have a spring force going upwards. And then what else?
Gravity.
And if this thing is at rest, not accelerating, what's the sum of those forces?
Zero.
Zero.
Good. So the sum of forces in the y direction would be the spring force minus mg. And that's equal to 0, ma. And so this means that the spring force would be equal to mg in this case, right? So let's go ahead and see if we can find the spring constant from looking at this. I'm going to erase this. So if I take that formula for this, this is the magnitude of the spring force, by the way. So the spring force in the y would be, in the y direction would be minus k times the stretch in the spring. For a 50 gram mass, this was 2 inches. Right? But the magnitude of this would be k times 2 inches. That thing's an inch, right? How can we convert, let's convert that to SI units. How do we do that? Yeah, so this would be k times 2 inches times 2.54 centimeters is 1 inch times 1 meter is 100 centimeters. And so what would that be? K 0 point, whoa, sorry, I didn't hear.
5.05.
0.508, okay, good. Oh, 8 meters, okay, okay. And so this would have to equal mg, wouldn't it?
Mhm.
So K times 0.0508 meters is equal to mg, which is 0.05 kilograms for a 50 gram mass, times 9.8 meters per second squared. And so if I wanted to solve for K, I'd just divide by that length, wouldn't I? .05 kilograms times 9.8 meters per second squared divided by 0.0508 meters. And what do you get?
-9.6.
Negative 9.6. Well, actually, it'd be I mean,
Yeah.
spring constant is positive, right? The negative sign gets put is from here. So if we're looking at this magnitude of spring force, we just put the positive there.
So we don't need the negative for this one?
The negative just tells us that the direction of the spring force is opposite the stretch.
Okay.
And so if I'm interested in the magnitude of the spring force upwards, I just ignore that negative sign, okay?
Okay.
The negative sign is just for direction. By the time I move down to here, and then just looking at magnitudes of forces, I don't have to put in any further directions.
Okay. Okay.
So 9.6, and what would be the units on this?
Nothing.
Kilograms per second squared, it looks like. Those meters cancel, right? And this can be written as a Newton per meter. Newton's unit of force, meters of length. If I have force is Newton per meter times the length, I get all the units consistent. Okay. And that's one data point. If we can try this one, see if you get the same thing, and you will, of course. And in the lab, you'll probably do something like this in lab. A lot of times what we do, not this week, but next week, a lot of times what you'll do is you'll look at maybe length stretched versus applied force. So this would also be the force of the spring force, and you'll have various data points like this, and then you plot a line of best fit through here and figure out the slope of that line of best fit. If these are my data points, so Fs is equal to K times length stretched. So if I plot, these are on my x-axis, the length stretched. This is on my y. This is of the form y is equal to mx, like so. And this is this is the slope of the line. So that means that those two things are the slope. These two things, if I equate all of those. So if I plot the force versus length stretched and get the slope of that, I get the spring constant. Does that make sense?
Is that X final length?
X minus X minus, this is just the length stretched, okay? So if this is my initial length, before I add any weight, this is my final length after I add weight. This would be the length drift. And that's what I'm plotting on here, on the x-axis, that full difference.
And that line starts to flatten as we approach the limits of the situation.
Well, yes, so we have Hooke's law, this is called Hooke's law.
Yes.
It's called Hooke's law for springs. And Hooke's law works great for a wide range for springs, but at some point, by the time I'm starting to deform the spring, it starts to break down. That's beyond the elastic limit, we call it. Okay, does this make sense about the actual law of spring? You want to do some examples?
Yes.
I'll let you do some examples, and then we'll start doing what we call simple harmonic motion on Wednesday, I think. Okay, let's say that I have a block on a floor. This is a 10-kilogram block, and it's being dragged over a floor where the coefficient of friction between the block and the floor is 0.4. This is a horizontal floor. And it's being dragged with a spring, by a spring. The spring is stretched by 10 centimeters as it's dragging this block. And this V is equal to a constant. It's not accelerating. It's this way and it's equal to a constant. So it's at a constant velocity. Question for you. Well, do you want me to do this one first or let you work on it?
Doesn't matter.
I'll let you work on it for a minute or two and then I'll do it. Spring is stretched by 10 centimeters. Question is, what is the spring constant? And I'll let you work on that a little bit.
Sorry, Alyssa.